We often stare at our screens, see a loading error, and conclude that the internet is down. Usually, the physical internet connection is totally fine. The failure is actually happening in one of two distinct background processes. Those two foundational processes are DHCP and DNS. Because both protocols operate invisibly, and both will stop a device from browsing the web if they fail, beginners routinely mix them up. Guessing which one is broken leads to arbitrary hardware reboots. That wastes time, and if the issue is a local device configuration, restarting the router won't fix it. Look at this matrix comparing the two. On the left, DHCP handles your local identity. On the right, DNS handles your global navigation. If we trace the path down from an internet down symptom, the very first question is whether the failure is local or external. When a troubleshooting effort assumes the problem is on the right side of this matrix, an external navigation failure, while the actual issue is a missing local identity on the left, you end up attempting fixes that cannot possibly work. Understanding the strict division between local identity and global navigation is the only way to replace frustrating guesswork with a precise, rapid diagnostic process. Watch this smartphone screen. The moment a user taps a Wi-Fi network and that looping connecting animation appears, the initial input phase of networking begins. The device is reaching out to the Dynamic Host Configuration Protocol, or DHCP, to ask for the credentials it needs to exist on that specific network. The DHCP server responds automatically, assigning 4 specific settings: an IP address, a subnet mask, a default gateway, and the address for a DNS server. Without this automation, a user would have to manually type those 4 strings of numbers into every laptop, phone, and smart TV they wanted to connect. If a device sends out that initial request and the DHCP server is offline, unreachable, or out of available addresses, the process halts. The device eventually gives up and assigns itself a fallback address, specifically one starting with 169.254, known as an APIPA address. Your device might display a full set of Wi-Fi bars, but with a 169.254 address, it has no local identity. It is completely isolated and incapable of sending or receiving actual network traffic. The external navigation phase starts the second a user types a human-readable domain name, like youtube.com, into their browser. Routers and switches cannot process words. They only know how to forward traffic to numerical IP addresses. The domain name system, or DNS, intercepts that human-readable word and translates it into the precise destination IP address the network hardware requires. This translation introduces a microscopic lookup delay. In exchange, it eliminates the impossible burden of humans having to memorize strings of numbers for every website they want to visit. If the designated DNS server goes offline or actively blocks a domain request, the translation fails. In this state, the network itself is fully functional. A user could type an external IP address directly into their browser, and the page would load perfectly, but typing the domain name results in an error. This creates a confusing, half-broken state. Background applications that already know their destination IP addresses will continue running normally, while active web browsing comes to a complete halt. The main reason beginners confuse these protocols is that they are deeply intertwined. The DHCP server is the entity that hands out the DNS server address in the first place. This creates a strict chronological dependency. DHCP must succeed before your device even knows who to ask for a DNS translation. We can map this sequence with a restaurant analogy. Look at step 1 on this flowchart. A customer walking through the front door represents your device physically connecting to the network. In step 2, the host assigns the customer to table 4. This is DHCP giving your device its local identity, like the IP address 192.168.1.25. Moving to step 3, the customer looks at the menu and orders a burger by name. That is DNS, translating the human-readable request for youtube.com. Finally, in step 4, the kitchen processes that order as internal item number 42. This is the network sending your traffic to the actual destination IP address. Because the host at the front door hands you the menu, failing to get a table means you can never place an order. A DHCP failure inherently breaks the DNS process for that specific device. They perform completely separate jobs, but this chain dependency is exactly why a localized identity failure is routinely misdiagnosed as an external internet outage. Approaching a broken network methodically requires testing these protocols in the exact order they operate. Look at this diagnostic checklist to verify local identity first. Step 1 asks if the device has a valid IP address. If it starts with 169 or is blank entirely, you have a DHCP failure. You stop right there. If the IP is valid, Step 2 verifies local routing by checking if the device can reach the default gateway. Step 3 tests external resolution. If the device can reach an external IP directly, but a domain name fails to load, that confirms a DNS failure. Running these checks in sequence prevents a technician from wasting time troubleshooting external servers or replacing cables when the device simply lacks a local identity. For IT students preparing for certification exams, understanding this sequence is a heavy point scorer. Exam questions regarding the OSI model or troubleshooting sequences require you to know that DHCP configuration must chronologically precede any DNS request. For the home user or small business owner, the stakes are measured in uptime and sanity. Watch this user ripping cords out of the wall, taking 30 seconds to open your network settings and check for a valid IP address, which prevents hours of this exact kind of frustration. DHCP gets the device connected to the local environment. DNS gets the device to its external destination. Applying that distinction is what separates reactive guesswork from targeted problem solving.